So, in the last video, I left off mentioning John Ioannidis. I'm sure I've never pronounced his name correctly. Apologies to anyone of Greek descent that's noticing I'm very, very wrong. But anyway, he published a very influential paper in 2005 that was kind of an existential wake-up call for a lot of people in different scientific disciplines. But in a lot of ways, it was kind of ignored, even though I don't know if many people really disagree with many of the outcomes of it. So, this paper was called very inflammatorily to get attention for good reason, why most published research findings are false. So this is kind of a scary thing to hear for scientists, right? Um, but he based his estimates and this evidence on the idea that when we have a lot of these different features of a research area or study designs, the findings that we are reporting are just generally likely to be less true. If you have small sample sizes, your estimates are going to be less stable. If your effect sizes are small and closer to zero, then those differences that you're estimating, they might not be real. They might be equivalent to zero in a lot of ways. When everyone is tackling new research questions and not replicating other people's studies, then we don't really have the ability to accumulate literature, like to do a meta-analysis to see what an average effect size is. So if everyone's trying to be original, then we don't build up that information. And we've talked in this semester about how there's a lot of choices you can make in your research design, and in some ways that's useful. But when there's unlimited flexibility in how you choose to define things and measure things and manipulate things and analyze things, then you can find support for anything if you just make different choices, basically. Um, and also, when there are financial incentives or other interests in the field, I mean, everyone has financial incentives to publish because they want to get and keep their jobs. And sometimes these, in psychology, they're more likely to just be that. But in other fields like medicine or chemistry or physics, there might be financial incentives like to patent something or to find a new way to, extract whatever resource we're interested in. And finally, if a field of research is like hot or sexy and people are trying to do new work in that area, then all these problems are going to be compounded in a lot of ways. So this kind of wake up call, it didn't wake enough people up, basically. But it's important to look back at this and show that these problems are not new in 2011 or 2020 or 2021. That we, need to be able to reckon with these things rather than just sticking our heads in the sand and saying, "Oh, it's not as bad as people say." It's maybe worse than people say. And a lot of these things that Ioannidis pointed out are things that we might call today questionable research practices. One paper that kind of coined, well, maybe not coined the term, but popularized it by surveying a lot of psychologists anonymously, John Lowenstein and Perlack. They wanted to estimate how frequent and prevalent these questionable research practices were among psychologists. And when they asked people, they had them admit to whether they actually engaged in these practices, how prevalent they thought these practices were among other people, like the field in general, and they use some kind of fancy math to estimate a more accurate prevalence estimate, given the biases that people have in their self-remission rate and stuff like that. So you can look at these things, but there's all of these things are happening to some extent. People are admitting to these things from 1% all the way up to the high 60s% for some of them. Failing to report all dependent measures. So, if you run a study and you measure your DV in 3 ways, but you only report the one that works, like that used to be very common practice. And it was easy to do a study and not tell people all the things you measured. It still is easy, but you shouldn't do that because that's basically doing 3 tests. Like with the dice metaphor that I use in inferential statistics, you roll the dice 3 times, you're more likely to get the number that you want if you roll it 3 times than 1. So you're just kind of inflating the likelihood you're going to get the result you want. Collecting more data after you see if the results are significant, you should have a cutoff point already that you have decided that's informed by the effect size that you expect to see by doing a power analysis rather than just saying, oh, it's not quite significant. If I add some more participants, maybe I'll get below that 0.05 level. The flip side of not reporting all your DVs, maybe not reporting all your conditions for your IVs, stopping your data collection. The flip side of this one, after you get the result you want, rounding down your p-values. So if I talked about that feedback I got from a reviewer before, where they said, nothing is highly significant, just say whether or not it's significant. It kind of fits in with that. If your p-value is 0.051, too bad, it's not significant. But people often round these things down. There's something called the file drawer problem that I've alluded to before, even in this series, I guess, where you do a bunch of studies and only one works, so that's the only one you try to get published. So only reporting the studies that worked, like presumably Daryl Bem did by finding evidence for precognition, that is a big problem. Taking out data after looking at the impact of doing so, say, I'm going to exclude, people from this demographic group or people that missed an attention check, but I'm going to run the data with and without them and report the one that helps me. Or claiming to have predicted an unexpected finding. People might call this today p-hacking, or hypothesizing after the results are known, I guess it would be more specifically about this. So you look at the results and say, yeah, I predicted that when you write your paper up. You should not be doing that because that's also going to increase false positives. Because if you're not predicting something and you're just saying that you did, you are probably capitalizing on chance in some way. Falsely claiming your results are unaffected by demographic changes, or just flat out falsifying data. So all of these things, as of 2011, when this study was published, are big problems. And these numbers have probably changed a little, but they probably have not changed enough. They should, ideally all be at zero, and they will probably never be at zero because of these easy ways we can put our self-interest in there. Other things they asked people were, how often do you engage in things that might undermine the integrity of your research? And the white bars are never. Gray bars are once or twice, striped bars are occasionally, and black bars are often. And so people, don't think that anyone's doing this stuff often, but look at the kind of the halo people are putting around themselves and their collaborators. 65% or so of people are saying that they and their collaborators never engage in these practices, but they're saying, well, other people probably do once or twice or occasionally. Both of these things cannot be true, right? So there probably is kind of an above average effect or some kind of desirability in reporting these things where more people are doing this than are willing to admit it. So this is part of how they calculated those expected percentages on the last graph. So these are things that people know are wrong because they're not admitting them, and they're ashamed of them because they know they're distorting the things that we see in the scientific literature. So around the same time, some other researchers that some of them are kind of self-proclaimed data detectives that look at a lot of papers and try to determine, if people are above board in the way they're reporting things. They conducted a couple of studies that they reported that claim to show that certain songs can change the ages or subjective ages of listeners. So bear with me while I kind of explain what they did here. The first study, musical contrast and subjective age. They had 30 undergrads listen to either a control song, I think it was like the music from preloaded on some Windows version a million years ago, or Hot Potato by the Wiggles. So they're saying, listening to a song for young people is going to make you feel old, essentially. So they had people listen to the song and then report what they felt, and they had people report different things so they could control for the baseline age of participants. And when they did this, they found that people felt older when they listened to Hot Potato compared to the control song. They felt significantly older, reported here, the p-value below 0.05. So, that's an interesting finding that makes people, feel older, somewhere moving from close to the young rating here and the control condition to somewhere between young and the middle condition here. So that's possibly interesting, right? They also ran another study where they showed that certain songs can actually change the ages of listeners. So they had 20 undergrads listen to either a control song or When I'm 64 by the Beatles, a song that might make you feel kind of old. or make you feel younger, depending on what you find. And they found that people that listened to When I'm 64 became younger or were younger. This is an experiment, right? They're randomly assigning people to a condition, and they're finding that less than 0.05, the likelihood that this is due to chance. People were a year and a half younger compared to when they listened to When I'm 64 compared to a control song. So these studies are obviously garbage, right? Especially the second one. Like they cannot change people's ages by making them listen to one song or another. They actually conducted these studies. They really did. And they used normal statistics. They reported their results as truthfully as we would expect people to in a lot of the studies published around or before this time. But what they did was they used questionable research practices. That's what happened. So, just an example from study 2 here. The stuff in bold is what they, reported about what they did, what I told you. And the stuff in gray is stuff that they also did in study 2 that they didn't report. So they cut down the number of participants to make it significant. They actually had a third condition, the Wiggles song condition. So they had an old control and young song. They did analyses after about every 10 participants to just see when it was significant. They asked them a bunch of other things and then just controlled for the age measure that helped their results. They had people, they controlled for it and ran it both ways and just reported the one that actually worked. So adding that control of the father's age. So they did this on purpose, right? To show you that you can make these results say whatever you want if you are willing to do a bunch of stuff and then not report it. And a lot of people probably were and possibly still are, likely still are, doing some of these things. And they also, ran some computer simulations to show that if you do these 4 things, have 2 dependent variables and only report 1, have add more observations to try to get your p-value down, controlling for gender as a demographic variable, or dropping or not dropping one of your conditions, that's going to increase the likelihood that you observe a significant result below 0.05. And this you see this 0.05 result actually being a 9.5% result. This is in line with what I showed you with that dice rolling task, right? If you roll the dice twice to get the same number, it's basically going to give you almost a double chance of finding this. And all these decisions are going to increase the likelihood that you're going to find a p-value less than 0.05, but it's not actually a 0.05 or a 5% chance, right? Because of these decisions. And if you do more than one of these things, it skyrockets. So if you did all of these things, you would have a 60% chance, almost a 2/3 chance of finding a p-value below 0.05 if you did all these different decisions and just let the results say what you wanted. So this is a huge problem. This is something that we are still grappling with as a field, and that I think it's really important to tell people about as undergrads so you can have an understanding of this and be skeptical about things that you read. Not cynical, not believing that it's all meaningless, but be skeptical so you can be people that understand how problematic and important this is. And I think it's worth reading part of Simmons, Nelson, and Simonson's conclusions because they worded it, I think, better than anyone really can. Our goal as scientists is not to publish as many articles as we can, but to discover and disseminate the truth. Many of us, and this includes the 3 authors of this article, often lose sight of this goal, yielding to the pressure to do whatever is justifiable to compile a set of studies that we can publish. This is not driven by a willingness to deceive, but by the self-serving interpretation of ambiguity, which enables us to convince ourselves that whatever decisions produce the most publishable outcome must have also been the most appropriate. This article advocates a set of disclosure requirements that imposes minimal costs on authors, readers, and reviewers. These solutions will not rid researchers of publication pressures, but they will limit what authors are able to justify as acceptable to others and to themselves. We should embrace these disclosure requirements as if the credibility of our profession depended on them, because it does. And I think that is, again, just a very powerful statement about what we can do. So the next video, I'm going to talk about what we can do and what groups and individuals are doing to promote these kinds of practices.